We have a few basic equations for electromagnetic waves, or a little bit more commonly said as light. And we want to go over and try to develop a little intuition and facility with. So the first of these relationships for light is called the simple wave equation. And the simple in the simple wave equation means that the speed that the wave propagates at is independent of wavelength or frequency. So it's not the way all waves are, but that's the way a lot of them are. Sound waves, waves of light, all would be a simple wave equation. So simple wave equation tells us wavelength times frequency is going to be the speed of the wave, and all across the electromagnetic spectrum, it's the same speed, the speed of light. So it doesn't matter gamma ray, X-ray, ultraviolet, visible light, infrared, microwave, radio, all travel with the same speed, c. So lambda, lowercase lambda, is wavelength, and we would normally measure that in meters, although sometimes we might use nanometers or micrometers or millimeter or some multiple of meter to make the number a little bit more convenient. F is frequency, and that is measured in hertz. And 1 hertz means I have a pattern that is repeating once every second. So you can think of a hertz being cycles per second, and the number of cycles is a pure number, so it's just 1 over a second. And then for our simple wave equation, the other thing that we need is the speed of light. Lowercase c, 3.0 times 10 to the 8th meters every second, speed of light. And this is actually known and defined to be an exact value, but for purposes of this class, 3.0 times 10 to the 8th is good enough. All right, so what does a simple wave equation tell us? Well, the product of wavelength times frequency has always got to be a constant. So if I have a very high frequency, I must have a very short wavelength. If I have a very long wavelength, that must come with a very low frequency, because the product of the two has always got to work out to be the same value. The other relationship that we're going to use is how much energy is in a photon. And a photon is a packet of energy carried by light. It's a quantum of light energy. So the energy in a photon is a constant, lowercase h, times the frequency. If instead you're given the wavelength, I can substitute in that the frequency is going to be c over lambda. So I could write this then as hc over lambda if you want. All right, so the intuition from this relationship is that the higher energy is going to come from light that has the higher frequency. So ultraviolet light carries more energy per photon than visible light. X-ray light carries more energy per photon than ultraviolet, and gamma rays carry more energy per photon than X-ray. So I go to higher and higher frequency, I have higher and higher energy per photon. All right, let's go through what all these variables are. E is energy of 1 photon in joules, Joule, nothing to do with vaping. Sounds the same, not the same. 1 joule of energy corresponds to an energy of 1 kilogram meter squared per second squared. Lowercase h is Planck's constant, which sets the scale for quantum phenomena. It's a very small number, 6.63 times 10 to the minus 34, and it is in units of energy times time. So that's joule second. And that is Planck's constant. And F is the frequency in hertz, just like we had above. Another thing I'll make a note of, sometimes you might see reference to a photon. Oops. So a symbol for a single photon is a lowercase gamma. All right, so let's try a few examples. Let's try a case where we're trying to solve for the frequency given the wavelength. So for this example, we're going to use where the spectrum of thermal radiation from the sun peaks at, which is at a wavelength of 500 nanometers. Now, the speed of light is not in nanometers, so I'm going to have to convert this before I do a calculation, or else I'm going to be off by a bunch. So 500 nanometers is 500 times 10 to the minus 9th meters. Because a nanometer, there are a billion nanometers in 1 meter. And that is going to work out to be, if we write it in our normal scientific notation form, 5.0 times 10 to the minus 7 meters. We want to know what the frequency of one of those photons is. Frequency is going to be c over the wavelength, speed of light over lambda. So we've got 3 times 10 to the 8th meter per second over 5 times 10 to the minus 7 meters. It's going to give us a frequency of 6 times 10 to the 14th. Well, and it's going to be inverse seconds because the meters cancel out. And that is telling us that the frequency is 6 times 10 to the 14 hertz. All right, an example using the relationship for the energy in a photon. So we take this same frequency and we're going to ask how much energy does a photon at 500 nanometers carry. So the energy of a photon, E, is Planck's constant times frequency, 6.63 times 10 to the minus 34 joule second times 6.0 times 10 to the 14 inverse seconds. So second and second cancel out. And we'll have an energy in joules, and it is going to be teeny, teeny, tiny. So the energy of one photon is 3.98 times 10 to the minus 19 joules. All right. Tiny, tiny energy in one photon of light. Now, if you have persevered in this course so far and have still refused to use scientific notation, I am going to personally wish you good luck writing this out correctly and doing mathematics with it in decimal form. Having 33 zeros and then 663, and using that in your calculator, or even worse, pencil and paper. Okay. Scientific notation makes all of this easier. It is no more difficult for me to write out this tiny value for Planck's constant as it is for me to write out this wavelength or this speed of light. Everything is on the same footing. So I don't look at a number like that and think, oh my God, what do I do? You just treat it like you do any other number. It's one of the virtues of scientific notation. Everything is on the same footing. It lets you think about things in a little bit different way. All right, the last thing we want to do is think about how many photons are being emitted by the sun every second. So, luminosity of the sun, 3.85 times 10 to the 26th watts. So 3.85 times 10 to the 26 joules of energy every second. And that is making use of 1 watt is energy flowing at a rate of 1 joule every second. So the sun is like a 3.85 times 10 to the 26th watt light bulb. So the number of photons that the sun is emitting every second is going to be the rate that the sun is radiating energy times a second. So an energy divided by energy per photon. So 3.85 times 10 to the 26 joules in a second of time. And each one of those photons, on average, 3.98 times 10 to the minus 19 joules, because the packet of energy is very, very, very small. Joule cancels out joule, and we just get a pure number of photons. So every second of time, the sun is radiating something like 9.67 times 10 to the 44th photons of light, or that's approximately 1 times 10 to the 45th. This is actually sort of a rough number because we're just using average energy per photon, and for that average we're taking where the thermal spectrum from the sun is peaking at. So this is truly a huge number of photons, in part because the sun is just stupid bright, and because the quantum scale is very, very small. So that energy that is being carried by light away from the sun is quantized into very, very, very small packets of light energy, and therefore we have a very large number of photons coming from the sun every second. And that number is so large that it's no wonder that any time you've been interacting with light in your life, you are thinking of light as being continuous and not quantized into little packets, because that is truly an astronomical number.